So the last thing that we're going to do with the precipitation reactions and solubility is how we can do calculations of these and actually apply them to concepts we've already seen. So let's work out an example. So the question is, if 500 mils of 0.100 molar ammonium chloride, this is aqueous, is added to 500 mils of 0.200 molar silver nitrate, aqueous. A precipitate forms. That's not a question, that's just a statement. We know precipitate forms. So the first step is, or the question is, to write the total ionic equation. And so that's going to be taking each of these. NH4Cl aqueous is actually NH4 plus aqueous plus Cl minus aqueous plus Ag plus aqueous plus NO3 minus aqueous. And then they would form, I'm going to do it all below because I ran out of room. First, I'm going to put the solid. And so I know that the precipitate would be between silver and chloride because they're insoluble. I also know that ammonium is never a form of precipitate, as well as nitrate. They are soluble with everything. So the only potential things that could form a precipitate were silver chloride. And then what we have left is ammonium aqueous plus nitrate aqueous. Okay, so this is the total ionic equation, but we remember with the total ionic equation, to get to the net ionic equation, we simply take out spectator ions, or another way to do it, so this be, right, the net ionic equation I like to just write out the solid first, silver chloride, and then just write on the the reactant side, well, what are the two ions of that? So that would be Ag plus aqueous plus Cl minus aqueous. So that's the net ionic equation. And then we can continue calculating some things in terms of concentration. So, so this is actually seems like a simple question, but it's actually not. So what is the total ion concentration once the solutions are mixed? So what that means is that we have some of the ions that are going to crash out. So we have some ions that are going to crash out to form a solid. And so we have to figure out. So if we look at what is the total ion concentration, well, that's going to be equal to the moles of our spectator ions we started out with. So that's N is for moles, NH4 plus moles of NO3 minus plus the excess, the amount of silver or chloride. We can't have both. I don't know what they are. So I'm going to put moles of excess ion. So this is going to be either, so we're going to run out, so in this reaction, we are going to run out of either silver or chloride, and that's going to limit how much silver chloride we can make. So it's going to be either moles of silver or moles of chloride. So we have to figure out which one will run out first, and then how much would be left over of that next. So this actually, to determine this is a limiting reactant problem. So that's why it's kind of trickier than it might initially look. And then this is liters of solution. So this total liters of solution. So what we're going to do is we are going to go do 3 steps. We're going to do step 1, step 2, and then the big step is step 3. So let's do step 1 first, which is finding the moles of the spectator ions. And so if we look up here, we're going to be using the concentrations and volumes. So concentration of NH4 plus comes from this volume and this concentration. So we can multiply those together to get the moles of NH4 plus. So we'll find moles of NH4 plus is equal to the molarity of NH4 plus times the volume of NH4 plus. So we know that the concentration of ammonium chloride was equal to 0.1 molar. Okay, and we know that for every 1 mole of ammonium chloride, we get 1 mole of ammonium. So that means that the concentration of ergo, therefore, concentration of ammonium chloride equals the concentration of ammonium. So we can say the concentration of ammonium is 0.1 molar. So 0.100 molar, and the volume was a half a liter. Make sure you use half a liter here and not 500 so that the units in molarity cancel out, and we're left with moles. So this is going to be 0.0500 moles of ammonium. So we've done part 1. We then are going to do part 2, which is going to be the moles of nitrate. So moles of nitrate, which is equal to the molarity of the nitrate ion times the volume of the nitrate ion. Okay, and very similar, if we look up here, moles of nitrate, now we have, it's a 1-to-1 relationship. So if I have 0.2 molar silver nitrate, I also have 0.2 molar nitrate. So for the same reasons that we stated here, we are going to put in 0.200 molar, and that was also a half liter. And so in this case, if we do that calculation, we get 0.100 moles of nitrate. So we've done parts 1 and 2. Now to figure out part 3, that's going to be the moles of ions in excess. We have to find moles of silver, find moles of chloride, and then figure out which one is limiting. So if we look up here, we had so if we go here, we have ammonium chloride. So it's a 1-to-1 relationship. So if I have 1 mole of ammonium chloride, I would have 1 mole of ammonium and 1 mole of chloride. That means that my calculated value of ammonium would also be the calculated moles of Cl-. And so I can write that here. So I can say that here, the moles of ammonium equal the moles of Cl-. And I already calculated that the moles of Cl-, or the moles of ammonium, are 0.0500 moles Cl-. And the same is true for silver nitrate. So we have silver nitrate. If I have 1 silver, I have 1 nitrate. So then the moles of nitrate I already calculated are equal to the moles of silver. So moles of nitrate were 0.1 mole. So I can simply say that moles of nitrate equal moles of silver equal 0.100 moles silver. Now, you could have easily done these calculations. You could have done these exact same calculations again. I could have done this calculation and this calculation again, but for silver and chloride, but there's no reason to if you kind of see what's going on there. Now, if you look here, we can see that silver chloride is a 1-to-1 relationship. That makes it easy, and I can see that I have less silver. So this is my limiting reactant. And so this will be in excess, so I'll have Ag in excess. So how much I have left over is pretty easy to find. It's just going to be, so moles Ag plus in excess is simply how many moles of Ag I started with, which was 0.100 moles, minus how many moles of Cl minus we were going to use, which is all of them, which is 0.0500 moles. And so we find that the moles of Ag in excess is 0.0500 moles Ag plus in excess. Okay. So then to finish this problem, we are going to basically put everything back into this equation. So I'll rewrite it. So the total ion concentration is equal to moles of ammonium plus moles of nitrate plus moles of silver in excess divided by the total volume, which was 0.5 liters plus 0.5 liters. So moles of nitrate, moles of ammonium were 0.0500 plus moles of nitrate, which is 0.100, plus moles of silver, which is 0.05, divided by 1 liter. And then these are all moles. So then your new volume would be, or new concentration would be 0.2 divided by 1, which is 0.200 molar ions, which is the total ion concentration. Now, this is honestly one of the hardest problems that we could do in this class, simply because it's combining two different concepts together, combining the idea of a limiting reactant problem with doing lots of calculations that you can make a simple mistake. It's a favorite problem of mine, simply because it covers a lot of chemistry that we've talked about in the class, and so it tends to end up on assessments. So just pointing out that there is a stepwise process to do this, and the total ion concentration makes sense because even though we didn't start off, we started off with a lower concentration of 0.1 and 0.2. We can end up with a concentration of 0.2 simply because for every solution, we actually had 4 ions, so the total ion concentration can be greater than the concentration of individual compounds, ionic compounds in a solution, or ions in a solution.